All right. Well, thanks for having me, and I hope everyone's having a good night so far. My name is Doug Klein, and I am a systems engineer at NASA's Jet Propulsion Laboratory in Pasadena, California. Um, so I grew up on the East Coast in New Jersey, not too far, similar area as kind of where you guys live in Connecticut, and went down to University of Maryland to get a degree in aerospace engineering. And after graduating, I moved out to California when I got a job offer to work on Mars rovers at the Jet Propulsion Laboratory. And so I've been here for just over 4 years now. And today I'll tell you guys a little bit about some of the work I've been doing. Um, so let me just switch over to my presentation. Let's see. Okay. Um, so I have been supporting various roles on the Curiosity mission over the last 4 years. I'm on the team of people that actually command all of the driving and move the arm and everything. So we're called rover planners, and it's been a lot of fun, kind of like driving a rover. I'm also on the sampling downlink team as well. So we do a lot of data analysis to try and understand what's been going on with the rover and how we can fix it when things go wrong. And so today, I'll give you guys a bit of an overview of the Curiosity rover and its mission and all the various tools it has, and why we're even there on Mars and what we're trying to learn. And then I'll tell you a little bit about the sampling system, which is really my area of expertise, and some of the problems that we've encountered and some of the really recent, exciting new achievements that we've been able to work around those problems. So the Curiosity rover is on Mars to search for environments that could have potentially been able to support life. So we're not yet a life detection mission, but we have a bunch of tools to do geology and chemistry and biology on Mars to try and understand if the area that we're in could have supported life at some point. And so we're looking for various things: water, the weather, radiation levels. All these things kind of contribute to us understanding if life could have ever been on Mars or could currently be on Mars even. So to just get a little bit of context, Curiosity is kind of the third generation of rovers that we are putting on Mars. The first one was Sojourner, and that was 21 years ago. And Sojourner was really just a technology demonstration. We didn't even know if it was possible or even useful to put something with wheels on to go drive around Mars and explore for us. And Sojourner was very successful. So in 2004, we followed that up with the Spirit and Opportunity rovers. So we sent two twin rovers, exactly identical, to different locations on Mars. And these were smaller solar-powered rovers, and we initially thought that because they were solar-powered, dust would settle on their solar panels and they would only have a 90-day mission. Turns out that Mars gets these little windstorms occasionally that can brush the dust off their solar powers. And so Opportunity is actually still operating on Mars, and it's been over 14 years now, which is pretty amazing considering that it just had a 90-day initial mission. And then in 2012, we landed the Curiosity rover. So just over 6 years ago, we had our 6-year anniversary was about 6 days ago or a week ago. So that was pretty exciting for us. And the important thing to learn about Spirit and Opportunity versus Curiosity is that Spirit and Opportunity you can think of as kind of a field geologist. So they could drive around Mars, take pictures, had a couple of tools to break apart rocks. The next thing that a geologist on Earth would want to do is take some samples and bring them back to their laboratory and do more in-depth analysis to try and see exactly what those samples are made of. And that's what Curiosity can do. So not only do we have cameras to look at everything, but we can actually collect sample from rocks and have instruments inside the rover to tell us in a lot of detail what those samples are made of, which is really important for understanding if life could have ever lived here. Because we need to know if it has the same types of chemicals and materials there as we found on Earth that can support life. So we have a whole bunch of instruments to do all sorts of stuff on Curiosity. Each of these is pointing to a different instrument that really has a unique purpose. But generically, there's kind of a few different categories of what we do on Mars. So some of our instruments are passive. And these are things like weather measurements or radiation measurements that are just constantly collecting data to help us understand what Mars is like, how much radiation is there, what the wind patterns are. And these types of instruments we've been sending to Mars for about 20 years now and landing them on different parts of Mars. So we're able to really kind of understand a little bit about what Mars is actually like to be on the surface. Then we have instruments that we call remote sensing instruments. So these are like our cameras, where without even getting too close to anything, we can take pictures and look at different signatures in rocks to try and understand what they're made of. And that's kind of what we do every single day as we're driving around Mars, to get an idea of what the real juicy, interesting stuff is and what's new and what we want to take a closer look at. And then about once a week or so, we'll actually stop the rover and unstow this robotic arm here. So this arm reaches about 7 feet out, and there's a whole bunch of instruments and tools and things on the end of the arm that we can actually place directly on the rock surfaces to take measurements and understand even better what those rocks are made of. And then lastly, we have a drill mounted at the very end of this arm here, and that drill can collect powder from rocks and deliver it to 2 instruments that sit in the front belly of the rover here, called SAM and CHEMIN. And those instruments, those are the geologist lab, where we really can do a lot of analysis to try and understand what these rocks are actually made of. And so we landed about 6 years ago, like I said, in Gale Crater here. So Gale Crater is this huge crater created by a meteor impact billions of years ago on Mars. And in the center of this crater is this massive mount called Mount Sharp, and it's about 18,000 feet high, which is huge. The largest mountains in the lower 48 states are about 14,500 feet high. So this is a really, really big mountain that we're climbing. And the reason why we chose this site is because geologists and scientists really love to see elevation changes as we're climbing mountains or looking at crater walls, because each of those elevation changes tells us a little bit something about a different time period in Mars's history. And so what the previous rovers were able to do, Spirit and Opportunity, was to understand that Mars was actually, even though it's this cold desert now, with very little environment and atmosphere, it actually once had an atmosphere and was a lot warmer and wetter, and kind of was similar to what early Earth might have looked like. What they couldn't tell us is what happened to that condition, and not only was it wet, but was this water that could support life, kind of like we know lakes and oceans on Earth, or was this some really nasty, salty solution that could have never supported life? So those are the big questions that Curiosity set out to answer when we landed in 2012. And so this little circle here is roughly where we landed, which positioned us to start climbing this mountain. So here's another look at that. This is an overhead map of where we've been traveling to Mars. And so far in 6 years, we've traveled about 12.5 miles. And we started off up in this top right corner in Yellowknife Bay. And that area alone kept us occupied for about the first year of the mission or so. We had landed kind of in the stream bed and followed that stream into what was a shallow lake we had determined, and were right off the bat able to answer some of the biggest questions. So we drilled into the rocks at the bed of this lake and found those rocks contained the right chemistry that could have been hospitable to support life on Mars at some point. So similar to the types of materials that we might find in a freshwater lake on Earth, we found on Mars, and that was amazing to find in our first year of the mission. The second year of the mission, we did a lot of driving. So we went all the way from Yellowknife Bay, across these plains here, down to Pahrump Hills. And Pahrump Hills is really the base of Mount Sharp, the foothills, so to speak, where we really started climbing the mountain. And so once we got here, we started sampling a lot more regularly to try and understand each of those layers. And this is kind of when I joined the mission. So the first 2 years I was finishing up college, and right around when we arrived at Front Hills was like my first month of work, which was pretty exciting coming on board as a sampling engineer. We're finally getting to some of the really exciting parts of the mission for sampling. And this big X is where we are now on Vera Rubin Ridge. Um, and so there's really been a lot of changes here in different formations in the rocks as we've climbed. And so to look at this another way, here's a side profile of what we've been doing. So you can see the first, half a mission or so, or even more, 75% of the mission, has not really been that much elevation climbing. And now, just over the last couple of years, we are climbing this mountain and gaining a lot of elevation. So here we are, again with the red X here, and we're really getting close to some of the most exciting parts. This hematite unit is this really hard ridge that's formed on the mountain, and then beyond that is this clay unit, which we know on Earth clay is formed at the bottom of lakes often, and so that's going to be particularly interesting for us. And this is my favorite view to explain what we've been doing on Mars as a sampling engineer. So this shows every hole that we've collected sample from on Mars. So there are 17 so far. Our 17th we just collected on Thursday. So I don't actually have an updated graphic with a picture of that one. You can see that one's just fresh. So that was really exciting for us. But there's a couple things that are interesting about this. So if you look in the bottom left of each of these instruments, we have a sol number. So a sol is a Martian day. It's about a half hour longer than an Earth day here. And that's how we track time on Mars, is how many sols since landing. So we landed on sol 0, and right now it's about sol 2,140 or so, just after collecting this sample. And if you look at these sol numbers, you can see that we were collecting samples maybe every 3 months or so towards the beginning. And just at the end, or towards the end of these, we started to really pick it up a little bit. These two, Lubango and Okaruso, less than 2 weeks apart. So as we're climbing this elevation, we're really trying to capture a sample at every layer. And you can see these last 4 here or so, we're basically 1 a month. So we had decided about 2 years ago that we were going to collect a new sample every 75 feet of elevation change. So every couple weeks on Mars, we were climbing this mountain, and we wanted to understand exactly how the rocks were changing. And then the other thing to notice is that this one, Sabina, was collected on sol 1495. Duluth, the next one, was collected about a year and a half later on 2057. So something happened there that prevented us from being able to collect samples for about a year and a half. And then just recently, this spring and summer, we finally collected 2 more samples and have restarted that cadence of regularly sampling. So one thing that I'll talk about in a few slides is what happened there and how we were able to restore the sampling capability. So I won't go into too much detail on the sampling system, but just to give you a little bit of background about how this all works, there's 5 major components to the sampling system. So we have this big robotic arm. It's kind of like a human arm. It can move around and place things on the ground and everything. And that's about 7 feet long, as I said. Then we have this brush here called the dust removal tool. And so Mars is really dusty and kind of rusty. And so oftentimes when we look at rocks, we want to brush off the surface to see what the rock looks like and not what the dust that's covering Mars looks like. Then the other main component is the drill, which is kind of the backbone of this entire thing here. That drill is a really special drill. So it's not really like a hand drill that you might use at home when you're doing woodwork or something. It's a rotary percussive drill, so it's a lot more like a jackhammer or a masonry drill if you've ever used those, where it's kind of beating into the rock and percussing into it and pulverizing that rock into a fine powder, and then collecting that powder that it generates. Once it's collected that powder, it moves it over to a tool we call Chimera, which sieves that powder through 150 micron sieve, so we're getting just really, really fine particles, and then delivering a sample to our instruments that are about half the size of a baby aspirin pill. So this whole thing is incredibly complicated. There's 17 actuators involved, these 5 different groups of mechanisms, and the chief engineer of Curiosity during development said that he thought that this was perhaps one of the most complicated mechanical engineering challenges in all of JPL's history. So it was challenging for the team to build, and as we'll get into, it's been challenging for us to operate as well, but has also provided us with some of these amazing results. So just to give you a better idea of what sampling on Mars actually looks like, these holes are about the size of a nickel, and they're about as deep as your index finger. So just about 2 inches deep or so, a little bit deeper than that. And all we're really after is just collecting this powder from the bottom of the hole. And that's interesting for us, and it's important to get below the first surface of Mars, because that first surface has been exposed to radiation for billions of years. And so to really understand what these rocks are made of, and what could have been going on there in the past, we need to kind of get just below the surface and collect material there. So on the top left here is a picture of the drill bit. So it's more of a chisel bit and not like a cutting bit that you would use in wood. And then on the bottom left, we also have a scoop on the robotic arm as well. And 3 times now, we've been at these sand dune sites. Mars has these huge sand dunes, kind of like you might see in the Sahara Desert or something. And we've scooped sand from them and also analyzed those samples as well. So a lot of people think that roving Mars, nothing ever goes wrong, and I wish that was the case. But we have what we call anomalies, or problems that occur all the time, where things surprise us and things stop working the way they were supposed to. And so that's some of the fun as working on the operations team, is really understanding these problems and trying to figure out how we can still do our mission in the face of some of these problems. And so kind of grouped by those groups before, I've listed here the sols where all these problems have shown up. So you can see, across the whole mission, there's been these problems coming up. And they range from things that take us a couple hours to understand and we're ready to go the next day with our full mission, to things that really cause us to stop what we're doing and understand what's going on. And in some cases, like the drill, even resulted in us not being able to sample for a year and a half. So the red ones are those types of problems that really cause us to not want to use something until we have a new workaround or something. And, that can range from a couple of weeks to, as I said, over a year. So zooming in on just the drill, and I'll talk a little bit about those problems, which is the second half of this presentation. So like I said, it's a kind of like a jackhammer drill. So as it's rotating, it's also percussing into the drill. And so there's a few different mechanisms, 4 mechanisms on the drill. The spindle is the rotate mechanism. So that's kind of what's used to not only cut, but actually collect material and pull it into the drill from the rock. The first major problem that we had on the drill was actually with the percussion mechanism. And so we were getting these electrical shorts that were occurring kind of on and off as we were drilling. And so we've developed a few workarounds for that, but they show up occasionally. It's still a problem that we have, but we've still been able to use the percussion mechanism to drill in the rocks. But the real big one that stopped us in our tracks was on Sol 1536, about a year and a half ago, with this drill feed mechanism. And so what the feed mechanism does is it moves the drill into and out of rocks. And on this next slide, I'll try and explain that a little bit better. So here, the drill bit is kind of in the center of these images on the left side. And you can see there's 2 stabilizers on each side of the drill bit. And so the way we drill is we place those stabilizers on the rock first. And that keeps the arm and the drill perfectly stable while we're drilling to keep the bit from walking around and everything. Kind of like when you're drilling something at home, you're going to use your arm to brace yourself to make sure that you're not wobbling around and that you're drilling straight into what you're trying to drill. And so that's the point of these stabilizers. And the feed mechanism just slides the drill bit into and out of the rock past these stabilizers. And so what happened on Sol 1536 is that we had commanded, we placed the arm on the rock, everything was normal, we commanded the drill to start moving past the stabilizers and into the rock, and nothing moved. So the feed mechanism was totally stalled, and we couldn't reach the surface because we were behind these stabilizers. And so we spent a lot of time trying to understand that problem. Took us most of last spring to just try and understand what was going on and if there is somehow a way for us to still use the feed mechanism the way it was intended just by changing how we control it. And ultimately had to give up on that. And so last summer is when this picture on the top right was taken, where we managed to get the feed extended fully past the stabilizers here, so that the bit could at least access the rocks. And so now us as engineers had to figure out, without this mechanism, 5 years into our mission, we need to completely redesign and refigure out how we're going to drill on Mars again. And the technique that we came up with, we call feed extended drilling, which is where we're actually not using these stabilizers at all anymore and using the entire robotic arm to push the drill into rocks and pull it back out after drilling, instead of using the initial feed mechanism as the intent was. So I have a couple videos here to show you a little bit about what those two techniques look like. This first video was taken about 4 years ago. This is actually like my first month of work, when we're drilling with the standard old technique, still using that feed mechanism. And so just a couple of short clips, but you can see we place those stabilizers on the rock first, and then we bring the feed down to make contact, and then the drilling begins from there. Here's a new video that was, I think, taken sometime this winter while we're testing out our new capability. And you'll see the differences here in how we drill now. So here, that drill is already extended past those stabilizers, and we're moving the drill bit directly onto the rock here. So now the bit is directly in contact with the rock and rotating and percussing. And then we have to pull out once we are in the hole, retract safely from that rock as well. And all that is done again with this huge robotic arm instead of the single mechanism designed specifically to do this. So that took us most of the spring and winter to test and understand how it would perform in various rocks and what could go wrong. And as engineers, we do a lot of that, of trying to understand everything that could possibly go wrong, and how we can predict those things and prevent them from happening. So we were up doing exactly what this video shows, testing out in our Mars yard with our twin rover on Earth, and just drilling tens of holes all fall and winter and even into the spring a little bit, to make sure that this was safe to do on Mars. And as I mentioned, in I think early April, we finally tried it out successfully on Mars and obtained the first sample in a year and a half. So that was really exciting for us. We're really proud that we're entering our 7th year on Mars with the full capability of the rover, especially considering that the 6th year we didn't do any sampling that entire year. And we're really excited because, as I had mentioned, some of the most exciting things to sample on Mars are just coming up. So we have that clay unit ahead of us, and things are really changing as we're changing elevation. So there's a lot that we're really looking forward to. And if you want to learn more, NASA's Mars website is a really good place to go to look at things going on with the Curiosity rover. And there's a lot of new press releases and stuff that we're always trying to keep up to date. And with that, I don't have too much else to show you, so I can take some questions. Let's switch back over to me, and I guess you can unmute me as well.
All right, we're unmuted. Do you have any questions?
So, as we've seen, since we're talking to you in California, there's a little bit of a feedback issue. I imagine there's a delay when you're talking to the rover on Mars. How do you do that? Does it take a while for each command you make to execute at Mars?
Yeah, that's an so it can take anywhere from about 6 or 7 minutes to over a half hour to get a signal one way to Mars. So if we were to sit there and just command each thing, it might take up to an hour for us to see what happened. So because of that, we can't operate command by command. So what we do is we build up an entire day's plan. So if you could imagine waking up in the morning and just having a very detailed instructions of what you're going to do that day. You know, sit up in your bed, take 3 steps forward, turn right, that sort of thing for your entire day. That's what we do every single day. So there's a team of about 30 people on Earth. Most of us located in Pasadena, but the scientists are located around the world at different institutions and universities and places like that, where we get together every day and figure out what happened yesterday, what's new in the images that we took yesterday, what do we want to get done today, and then put together the set of commands and sequences that do exactly that. We can simulate it on Earth and make sure that it's going to do exactly what we want it to do. And then at the end of the day, we send it up to the rover and hope that it does what it wants and what we want it to, and come in the next day and see how it went. So that's kind of how the cadence that we work in.
Wasn't there recently a big sandstorm on Mars?
Yes. So currently we have a huge global dust storm. And this is something that we've observed over the past 20 years, that every 5 years or so, these huge global dust storms cover the entire planet. And so we're in the middle of one right now. It's been about 2 months. And this is really important and kind of has a pretty interesting impact on the rovers. So the older rovers, which I mentioned, Opportunity, is still on Mars and we still operate it, is solar powered. And so when it can't see the sun because it's covered in sand and dust and everything, then it can't get enough power to actually operate. So we've just been waiting, and that operations team has just been waiting for the sand to die down. And it looks like it is starting to decay a little, so we think over the next few weeks, we're hoping to get back in communication with Opportunity and to continue that mission. But they've basically just had to take a 2-month break because their solar panels can't get enough energy from the sun. The Curiosity isn't powered by solar panels. It's nuclear powered. So we can still get enough power even if we can't see the sun. And there's still enough light coming through. It's just very kind of diffuse. It's like a cloudy day, basically, constantly. And so we're still able to operate. It has some impacts. We're a little bit careful with getting that sand on camera lenses and stuff. So we've been a little bit cautious with how we operate. But it has kind of impacted us a little bit, but not a ton. But yeah, good question.